Hi all, welcome to Refactor. In this video, we'll be learning about the third important algorithm in data structures and algorithms, which is insertion sort. Insertion sort is again very similar to bubble sort and selection sort, the similarities being that the array always remains divided into two parts, which is the unsorted part and the sorted part, and with every iteration the size of the sorted part increases and the unsorted part decreases. But there is one key difference between selection sort, bubble sort, and insertion sort, which is the position of the sorted elements is not fixed after each iteration. Meaning that what used to happen in bubble sort and selection sort is once we sort one part of the array, the position of those elements remained fixed. But in insertion sort, we do sort one part of the array, we continue to make one part of the array sorted on one side, but the position of the elements in that part can still change after we introduce all the elements. And in bubble sort and selection sort, when we started sorting, we used to pick the first element, and then we used to, during that iteration, after doing consecutive comparisons, we used to at the end pick the largest element from that list and put it on one side. Basically, we used to pick one variable, insert the first element, but later on, whichever was the largest element, we used to take that in the variable and then replace its position. But in insertion sort, when we do the iteration, we all the time pick the next element, just the next element, and we will place it in the sorted array wherever it lies with respect to the elements currently present, right? So now let's see that in action what all of this means. We'll sort an array using insertion sort, and then we'll understand all of the logics related to insertion sort, right? So this is an array that we have. I've indexed it from 0 to 7. The length of the array is 8, and now let's solve it using insertion sort. So insertion sort, again, for insertion sort, since we have one part that would be sorted and then there's another part which would be used for picking elements from the array, so you can think there would be two variables involved in it. So that is something that we can think from here. Next is one element. So when we start the iterations, we always assume that the first element is sorted. So we do not start from the first one, we start from the second one, right? And the third point is, so we learned 2 points till now, that there would be two variables involved. That is, so this is just the logic building that I am telling before implementing, before learning about insertion sort. Second is we start from second index, not the first one. And if it's zeroth index, that would be the first one, but we do not start from the first element, we start from the second element. That is the second point. And the third point is that the elements in the start would be sorted, and we would be picking a new element. That is, we assume this is the sorted part, and we pick one element from here and we place it at its correct position with respect to the elements already present. So if you have a look here, we had 23 which we are assuming as sorted. When we start our iteration from the second element, then we compare 42 with 23. However, it's already at its correct position with respect to 23, to not do any swapping here. But when we move to 7 and so on, which are smaller elements, we would be doing some sorting. So let's deep dive and see how those swapping occur. So this is the first iteration where I equals to 1. So our first element is already sorted. We are at 42. Now what we do is for j equals to 2, we see whether this element 42 is smaller than 23 or not. If not, we don't do any swapping. So here we do not have it smaller than 23, so we will not be doing anything, no swapping, then for no change. So we'll simply move to the next iteration. So we move to I equals to 2. Here, now this is the state of the array for j equals to 1. Now this thing is, we are looking at the back left of the element. So we go by, if we are at the third element, we'll first check it with second element and first element, so on. So the indexing of j, how we're comparing it, would be reversed. So we'll go from j equals to 1 to j equals to 0, right? So we compare it with j equals to 1. At 1 we have 42. So since 7 is smaller than 42, we do the swapping. So 7 would come at 42th position, 42 would be moving to 7th position, right? And we go to the next iteration of j. Now we compare 7 with 23. Now since 7 is again smaller than 23, we do again the swapping, and this would be the final state of these three elements. We only iterate these three because we only have to compare this element with the elements which are present before it. So that was the second iteration. There is, since we have reached the end of the array, so we won't iterate further. We'll come out of the loop and then we'll move to the next iteration of the ith position. Now this is the state of the array, and our ith value of I is 3, so we are at 1. Now in j equals to 2, we would be comparing I with the element present just before it, which is 42. Now since 1 is smaller than 42, so we will be doing the swapping, and the position would be this: 1, 7, 23, 1, 42. Now in j equals to 1, we move to the next iteration, j equals to 1. We'll compare 1 with the element present before it, which is 23. Again, 1 is smaller than 23, so there would be a swapping. So after the swapping, the state of the array becomes this. So I'm just showing you the state of the first array, but the actual array remains the same. But we know, because we are starting from the third element, so the rest of the element beyond 3 would remain at their own position, and there would be only a change in the first half of the array. Now we have the position of 1 and 23, which is changed. We move to the next element before 1, which is 7. We'll compare 7 and 1. Again, 1 is smaller than 7, so we'll do the swapping, and this would be the final state of the array after the swapping. And again, now since we have reached the end of the array here, because j equals to 1, otherwise j would be equal to -1, we come out of the loop and we move to the next iteration. Now when we move to the next iteration, value of I equals to 4, which is, we are at 11. This is the state of the array and we are at 11. Now we'll be comparing, for j equals to 3, we will be comparing 11 with 42. Now since 11 is smaller than 42, we will do the swapping, and this will be the state. Did the swapping, right? Now we move to the next element, which is j equals to 2. For j equals to 2, we have 23, and then our next element is 11. Again, 11 is smaller, so we would be doing the swapping, and as you can see, the state of the array is this. Now for j equals to 1, we would be comparing 11 with 7, but this time 11 is larger than 7, so we won't be doing any swapping here, and we stop over here. We do not move any further. So our condition for returning back is whether we return the end, whether we reach the end of the array, or the element that we are comparing our current element with is already smaller because here 7 is already smaller than 11, so we stop here, we do not go any further, and we'll go to the next ith iteration. Now we are at I equals to 5. This is the state of the array, and we are comparing 9 now. Now we have to place 9 at its correct position. We compare 9 with its previous element, which is 42. Now we can see 9 is smaller than 42, so we swap it. And this is the state what is now. For j equals to 3, we'll compare 23 with 9. 9 again being smaller, we would be swapping it, and this is what the new positioning of the element should be. Now we move to the next element, j equals to 2. We compare 9 with 11. 9 again being smaller, we would be swapping 9 and 11, and this would be the state of the array. Now j equals to 1. We compare 7 with 9, but here 7 is already smaller than 9, so we do not move any further, and there is no change. We just return from the function. Now I equals to 6. This is the state of the array. We are at 18, the sixth element. We compare 18 with its previous element, which is 42. It is smaller, so it gets swapped. For j equals to 4, we compare 18 with 23. Again 18 being smaller, we swap. Now for j equals to 3, we compare 18 with its previous element, which is 11. Now it is not smaller further, so we do not change, and we move to the next iteration. Now the last iteration for I, which is 7, where we have reached the last element. We'll be comparing the last element with its previous element. So 3 is smaller than 42, so we swap it. For j equals to 5, we compare 3 with its previous element, which is 23. Again it's smaller, we swap. This is the state we reach. We reach the next jth location, next element, so we compare 3 with 18. Again smaller, we swap. Now j equals to 3. 3 is compared with 11. Again it's smaller, so we swap. Now move to the next element, j equals to 2. We compare 3 with 9. Again it's smaller, so we swap, and this is the state received. J equals to 1. We compare 3 with 7. Again smaller, so we swap, and this is the state. For j equals to 2, we compare 3 with 1. In this case, it is not smaller, so we won't be doing any swapping, and there would be no change further. So this was how we implement insertion sort. We pick one element, we compare it with the previous element, which we assume is in a sorted order. So if we find the previous element is smaller than the current element, we do change the positions, and if it is not smaller, then we assume that the element is already at its correct position with respect to the already sorted array. So we do not make any changes, and we move to the next element in the array. So that was how we implement insertion sort. Now let's just have a look at the time complexity. We'll have the look at the worst case complexity. So if n is the length of the array, if we go back at the iteration, we'll see in the first iteration we compare the second element with only the element present before it. So every time we are picking an element and we are comparing it with the elements that are present before it. So we would be picking each and every element one by one, but we start from the second element, not the first element. We start from the second element, so we would be doing 1 2 3 till the end of the array. So it will be like n minus 1 times we iterate for I, and then we iterate for j. So at every position we would be looking at all the elements present before that. So for when n equals to, basically I is equal to 1, we will be comparing one element because this is 0th index, so we'll be comparing one element. When I equals to 2, we'll be comparing with two elements before it. When we were here, so we compared with two elements. So you can see we had j equals to 1, j equals to 2. When I was 3, we had j equals to 2, 1, 0. So you can see every time we are doing comparisons n minus 1 into n minus 1 times. So let's go back to calculate the complexity. So it is like first time we did one comparison, second time we did two comparison, and so on. At the end we are doing n minus 1. So if you closely have a look, this is something equal to linear sum, which if you remember in our school we got learned the formula as n into n plus 1 by 2. And now this, if we evaluate, if n is very large, this would approximately be equal to O of n square, which is the worst case time complexity for insertion sort. Next, what is the best case time complexity? Best case time complexity for insertion sort would come when the array is already sorted. So if the array is already sorted, so what would happen is we would have to do the iteration just for I. Will not be needing, we'll be comparing it with the previous element, but actually we won't be doing any iterations further because we know it's already sorted. So we'll iterate over it one time for each element and then no further changes. So it will be, if we have n elements, we would be doing n iterations, and that is it. So we'll be running the loop n times, and therefore the complexity would approximate to O of n. That is the best case time complexity. But in interviews, if anyone asks, we only have to give the worst case complexity. This is only for comparing, while if there is any question which sorting algorithm is the best, so we always consider the worst case time complexity. But if the worst case time complexity is the same, then we consider the best case in order to choose which algorithm we need to use. So that is the only reason why we learn best case time complexity. Now the space complexity, so we did not really actually use any extra variables for solving our question. So the space complexity would be equal to constant space, which is O of n. If we had used any extra variables, extra memory for storing the array, then we would maybe have to change the complexity, but here we did not need that. So let's code insertion sort now. We have the function sorting and we have the array as the input variable for our function. We would be starting our first loop. Our first loop would have a variable I, but as I pointed out earlier, the ith variable will not be starting from 0 index, it would be starting from first index, because we assume that the first element is already sorted. So with respect to that, we start the for loop from the second element in insertion sort. Now we would be placing the element that we pick from the ith index in the variable insert. This is because later on we have to insert it at multiple positions based on wherever we find it fit. So it's like the temp variable that we maintain while swapping. So since we'll be swapping elements, we always need to keep this element. Now we'll be taking another variable j, which would be equal to I minus 1, because we have to compare it with the previous elements. Now since we have to compare it with all the previous elements, we'll be starting a while loop, and the condition for while loop would be till we reach the end of the array, or we reach the element which is smaller than the element which is present at insert, which means till insert is greater than the previous element, we'll continue with this loop. Like in the loop, we'll write the opposite condition only, because we are we have to continue the loop, so we have to continue the while loop till we are meeting the condition. So condition would be that insert is greater than the element which is present at j. So this is the condition for while loop, and till the condition meets, so what we would be doing, we would be swapping the elements. Swapping would be that we would be inserting the element which is larger at the position of the insert element, and insert element was initially present at input j plus I. So this is what we do, and in input j we would be putting insert, and we'll have to do a j minus minus. So what is happening here is we are just moving the larger element at the next index, and we are putting the insert element which we have to insert at the previous position. So we are just swapping the elements using this, and that is how it's solving the array. It will be sorting the array, and let's just run the code and see if it's working. So it has sorted the array in reverse index. Okay, actually the condition I used was the opposite, so we have to see till insert is smaller than the input j, so then we have to keep moving. So now you can see the correct answer is coming. So that you learned this also, that the same insertion sort can be used for sorting the array in ascending or descending order. So that was it for the code. I hope you got to learn something today. If you did, please do subscribe to my channel and leave a comment in the comment section below so that I can bring in more topics. Thank you so much. Have a good day. Bye bye.